Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at systems of linear equations. To start off with, I want to talk about what a system of linear equations is. We have already discussed linear equations. So if we have a system of linear equations, so we have two equations and each of those equations has two unknowns. So let's say we have x and y. When you're asked to solve that system, you're looking for the solution or the point or the set of values that satisfy both equations. So if we were to think of that in terms of a graph, if we were to draw the two linear equations, which would both be straight lines, what we would be looking for is the point where they intersect. So from this example, you can see that they intersect at the point 1, 4. So that's the set of values that would satisfy both equations, and that point would be on both lines. Normally, you're going to see one point of intersection, and therefore you will see a solution. However, there are three possible situations. The first is you have an independent and consistent system, which means that if you were to graph those two lines, they would intersect in one point. So there's a point of intersection, and that point of intersection would be the solution. So there's only one solution. There's only one set of values that will satisfy both equations. However, it's possible to have an inconsistent system. An inconsistent system, if we think of it graphically, it means that the lines will never intersect. It means there's no solution, and that happens if we have parallel lines. So you could encounter a system where there is no solution, and that would be explained by the fact that they're parallel lines and they will never intersect. The third alternative is that the system is a dependent system. And if we think of it graphically, what that means is that we have the same line. Both lines are the same. So all points on that line would be a solution of the system, which in real life, when you're looking at these applications, you're usually going to be working with an independent and a consistent system. But I want you to know that these exist and how to handle them and how to express your solution. We're going to take a look at the first method of solution, which is solution by substitution. You might be asked to solve these by graphing. I'm not going to show that because it's a very time-consuming and tedious and not very accurate method, but you might be expected to do that just to get an understanding of what the solution means. I'm going to not do it that method. I'm going to go on to the first algebraic method of solution, which is called substitution. So here we have an example of a system of linear equations. We have two equations, we have two unknowns, x and y. So I'm looking for the value of x and the value of y that will make this equation true and this equation true, and there should only be one set of values, unless we have the two systems I mentioned previously. The idea with substitution is you want to isolate one variable in one equation. When you have a coefficient of 1, that's easier to isolate than when you have a coefficient of something else. So I'm going to take this first equation and I am going to isolate this x by simply adding a y to both sides. So I'm going to take this equation and I'm going to isolate the x. I'm going to add a y to both sides, so I'll have x is equal to 10 plus y. Once I have that, I can very easily now substitute that in to my other equation, and that way I'll just have an equation with just y's in it. So I do a substitution, I get rid of the x, and I replace it with this expression. So my second equation is 3x plus 2y equals 20. So instead of an x, I substitute 10 plus y. Now I have an equation in which there's just one unknown, and I can solve that. So I'm going to get rid of the brackets first. I can combine 3y plus 2y is 5y. I'm also going to subtract 30 from both sides. So that 20 minus 30 will equal negative 10. And I'm going to divide both sides by 5. So y is equal to negative 2. We only have 1/2 of the solution. I need the value of x as well. That's going to be easy to find once I have my x isolated like this. So x will equal 10 plus the y value, which is negative 2. So 10 plus negative 2, x is equal to 8. That's the set of values that satisfies, we know it satisfies this first equation, but it should satisfy both equations. What I'm going to do is plug those values into the second equation just as a check to make sure that it's correct. So I'll do a check. Does 3 times x, which is 8, plus 2 times y, which is negative 2, does that equal 20? So I have 24 plus negative 4 equals 20. So I can see that it works. So this set of values, x equals 8 and y equals negative 2, satisfies both of these equations. Let's take a look at another example. In our next example, our variables are p and q, because when you look at the applications in different technologies and in business, you're going to see other letters other than x and y. So don't be intimidated by it. The process is exactly the same. But we have two equations in two unknowns. We're looking for the set of values for p and q that will satisfy both equations. To do the substitution, you look for the variable that's going to be the easiest to isolate, which means, if possible, the variable that has a coefficient of 1. If you don't have a coefficient of 1, you're going to get into fractions, and we want to avoid that. So we do have a q. It has a negative 1 coefficient. If we move it to the other side, it will be a positive 1, and then we can get q by itself. So we're going to add a q to both sides, and I'll have 4p equals 1 plus q, and then I'll subtract a 1 from both sides. So q will equal 4p minus 1. And if you can go right from here to there, that's great. I just didn't want to lose anybody. So q by itself will equal 4p minus 1. Now that I have one variable isolated, I'm going to substitute this expression into the other equation wherever I see a q. So I have 2p plus 5, and instead of a q, I have 4p minus 1. Again, this allows me to have an equation in just one unknown, which I am then able to solve. I can't solve it if I have two unknowns. So let's simplify this. 2p plus, that'll be 20p, minus 5 equals 17. So I will have 2p plus 20p is 22p. I'm going to add a 5 to both sides, so that will be 22. Divide by 22, and p equals 1. I'm only half done. I need to find the value for q. So I know q is equal to 4 times p. If p is 1, it'll be 4 times 1 minus 1. So q would equal 4 minus 1 is 3. So that should be my solution, but we want to check by plugging in to the other equation. I've used this equation to find q, so I shouldn't have to plug back into that one. I now go to the other one. So let's just do a check. Does 2p, which is equal to 1, plus 5 times q, which is 3, equals 17. So I have 2 plus 15. Yes, it does. So you know you've found the correct solution. If it satisfies both equations, then you know you're correct. Let's try one more. All right, in this example, we're back to x's and y's again. I'll bounce around a little bit. And we have 4x plus 5y equals negative 15, 2x minus 3y equals 9. None of these variables have a coefficient equal to 1. If I am going to do this by substitution, I'm going to probably work with the variable with the lowest coefficient or the easiest coefficient. So I would probably work with this one. I would first of all isolate 2x, and then I would isolate x, because 2 is the smallest or the easiest number of all of those coefficients. So I'm going to add a 3y to both sides. So 2x will equal 3y plus 9. Then to get x by isolated, I would have to divide by 2. So I'm dividing the whole side of the equation by 2. So you can do it like that, or each term divide by 2. We can use either of these expressions and then substitute it into the other equation. So because I isolated x using the second equation, now I'm going to substitute this expression into the first equation for x. So this equation, I will have 4 times, I'll use the second solution, 3 halves y plus 9 halves. Then that's just, I put that in for x. Then I have plus 5y equals negative 15. So now we need to simplify 6y, or in other words, I have 12 halves, which is 6y, plus the same thing here. I will have 18, because I'll either have 36 over 2, or I can cancel the 2 before I start and get 2 times 9. Plus 5y equals negative 15. I will have 11y. I'm going to subtract an 18 from both sides. And when I subtract 18 from both sides, I get negative 33. So y is equal to negative 3. There's my solution for y. I plug that in to this equation to find my solution for x. So x will equal 3 halves times negative 3 plus 9 halves. So x will equal negative 9 halves plus 9 halves. So x will equal 0. Normally I would then do a check back to this equation. Will 4 times 0, which is 0, plus 5 times y, which is negative 3, will that equal negative 15? Yes. You don't necessarily have to write your check unless your teacher asks you to. You can often, when your numbers are easier like this, you can often just take a look and see that. Now, it gets more complicated when you don't have a coefficient equal to 1, so that you end up with fractions. So in these kinds of systems, I have another algebraic method that I would probably use, and I'm going to cover that on the next video. So this method, substitution method, works really well when one of your variables has a coefficient of 1. If not, I would probably look at the next algebraic method to do the solution. But it's totally your choice, and practice some of these with substitution where it is fairly easy to isolate your variable. And then when you're comfortable and ready to move on to the next type, we can take a look at the next video. Until then, take care.